Welcome, welcome, welcome to another exciting day of AP Statistics. Today we're going to look at lesson 10.3. We're basically just going to kind of dig into significance testing a little bit deeper. Hopefully you'll have a better understanding of what it is and how to choose your alpha. But before we do that, because significance testing is so important to this class, we're going to do a few warm-up problems, just kind of practicing the skill, and hopefully after you try these on your own and get them right, you'll start to feel confident that you know how to do significance testing. All right, so here's a warm-up problem. All right, so we have a claim that average wind speed is 8 miles per hour. For some reason, somebody doesn't think that's accurate, so they go out and take 32 days as a sample size, and their sample yields an average wind speed of 8.2 miles per hour. And again, let's pretend we know the population standard deviation is 0.6. So what do we think? Is the average wind speed not 8 miles per hour as the researcher claims? Okay, so step one, we need to write our hypotheses, right? So our null hypothesis, the mean wind speed is 8 miles per hour. Okay, alternative, the wind speed is not 8 miles per hour. Okay, now it's important that you understand, again, this is a two-tailed test, because even though we have 8.2 as our sample, right, we have to cross that out because the alternative hypothesis would be written before we have our sample, right? Our sample can't lead us to a one-sided alternative. There's nowhere in here that says, hey, we think it's greater or we think it's less. So when that's lacking, it's a two-tailed alternative. Okay, also make sure you could write this in words, right? Null hypothesis, the average wind speed in a city is 8 miles per hour. Alternative, the average wind speed in the city is not 8 miles per hour, right? You will be asked to write it in words, so make sure you could do that. Okay, now we have the information we need. With 32 days, let's go through our checks, okay? Sorry, 0.6. Oh, and alpha, 0.05. Okay, so our checks. I'm assuming the city has been around for at least 320 days, so we can safely use our standard deviation formula. Okay, now let's talk about normality. We're talking about X bar. We have an N of 32. 40 is kind of that magic number that we like, but we'll say 32 is close enough for now. Again, in a future chapter, we'll talk a lot more about this. So we'll say the central limit theorem. Should give approximate normality. Of the sampling distribution. Of X bar. Okay, and then the other thing would be, do we have good unbiased data? It doesn't really say how the sample was obtained, but it doesn't, there's no reason to think that there's some bias in the wind, right? So unless the researcher purposefully picked extra windy days or something, we should be fine. We'll just say assume the sample came from SRS. Okay, so those are the kind of the three requirements, right? Good unbiased data, normality, because we're going to be using a z-score, and our population must be at least 10 times the size of our sample. Okay, so we've set things up, we've validated our calculation. Now it's time to do the calculation, right? So we got to get our z-score. Okay, and it's going to be two-tailed, so we're basically finding the probability that z, it's going to be 2 times the probability that z is greater than 8.2 minus 8, 0.6 over the square root of 32. A lot of students get hung up on the, why am I multiplying it by 2? Well, it's because it's two-sided, right? So we're somewhere over here. I don't know how many standard deviations because I haven't calculated yet, but we're somewhere over here and we're saying, hey, if we have any results over here, what's the probability of that happening if the 8 is true? Well, we would have accepted evidence on the other side as well because we said either direction. So what we do is we get the one side and then we double it, right? So let's work that out. I think I have it written down somewhere here. Yep, here we go. So working that out, we get a z of 1.88. And apparently we should get this. Okay. Which is above 5%. Okay, so we would conclude there's not enough evidence. Okay, but it's borderline, it's close, right? And by the way, how close is it? Well, you could look and compare the z-scores, right? We needed a z-score of 1.96. We got a z-score of 1.88. So we were close. We were really close, but not, we didn't get far enough away from the 8 to say at a 5% significance level that we could reject, okay? And this is actually something we're gonna talk about a lot today. Getting close, but not being able to reject. What does that mean? So anyway, our conclusion. If I could get the next page. Okay, so because our p-value exceeded our alpha, we don't have enough evidence to reject the null hypothesis. Doesn't mean it's true though, right? We had some evidence, quite a bit, just not enough. We were close, but not enough. Okay, so not enough evidence to reject the mean wind speed of 8 miles per hour. All right, let's try another warm-up. Again, pause the video, try it on your own, and then take a look if you got it right. All right, so this time we've got a report saying average age is 14 years. An airline executive does a sample of 36 planes, find the average age of his sample to be 12.8. So does his airline have planes that are newer than average? That's the question. Well, let's do our checks again. Well, first let's set up our hypothesis. So null hypothesis, the mean age is 14. Alternative, less than, right? It's right there, less than, so less than 14. Okay, our sample had a mean of 12.8. Our sample size was 36. And again, we're pretending we have sigma and the given alpha 1%. So pretty high level of evidence here. So our checks. Does the airline have at least 360 planes? That one's kind of uncertain, right? If it's a smaller airline, it probably would not. So we'll just have to assume this airline has at least 360 planes. So we can be safe using the standard deviation formula. Again, we don't know, and that's the point. We're telling whoever's reading our calculation that we're missing a bit of important information here, right? So take our calculation with a grain of salt. If it's really important, then do a little research and find out what company this is and if they have that many planes, right? Okay, again, we didn't hit 40 on our sample size. It'd be great if I had the data. I could graph it and see if it looked fairly normal or not, but for now, we're just going to say, hey, central limit theorem. So the central limit theorem should give approximate normality of the sampling distribution. And let's see, lastly, how was the sample selected? It doesn't say. We'll assume an SRS was used so that our calculation is valid. Again, if some other method were used, it could invalidate our results. And if it's important, you should, that's what we're telling the person who reads our work. If it's important, go investigate that. Depends how important it is, right? Okay, so there's our 3 requirements. All right, now this time it's a one-sided alternative. So find the probability that my z is less than 12.8 minus 14 over 2.7 square root of 36. Okay, so that'll give me my z. Again, I think I have it worked out already. So there it is. We should get a z of negative 2.66 and a p-value of less than 1%. Okay, and again, if you wanted to compare z-scores, you could see our z-star for a one-tailed 1% needs to be negative 2.33, and of course we've exceeded that, and that's why our p-value is less than our alpha. Okay, let me actually show you real quick on a calculator how you can get this. Again, you need to show the work calculating your z. Write down your z, and then to get your p-value, you could of course use a normal CDF, right? Okay, but we should also have a test, right? This is a z-test. Okay, in this case we have our stats. Okay, our null hypothesis is 14. Our sigma is 2.7. Our x bar is 12.8. Our n is 36. And we are doing a less than for our alternative. And there you go. Okay. Again, this is a quick, easy way to get the information you need. But you do need to show that bit of work. Okay. All right, so this time our p-value was less than our alpha, so we get to reject our null hypothesis. And whenever we reject our null hypothesis, that means we accept the alternative. Okay, so in this case, we get to say the company has enough evidence to say that the average age of their planes is less than the national average. Right? They could make that advertising claim. let's try another warm-up. Again, pause it if you need, try it on your own, and then see if you get it right. All right, this time we have a claim that the average cost of a paperback textbook is greater than $57.50. Notice the claim can be the null, the claim could be the alternative. It really doesn't matter. There's like, it's an argument, there's two sides. It doesn't really matter which person, presents you the argument, which side. Okay, we've got a sample, and we're gonna investigate that claim. All right. So null hypothesis. This person's claiming a cost greater than that, so the null would be, nope, it's not, right? It equals that. Remember, the null is always equal, and the alternative is always an inequality. In this case, greater than. Okay, all right, we've got sample mean. Sample size of 32. Again, sigma and an alpha of 5%. Okay, do your checks. All right, there's easily 320 paperback textbooks out there, so we can safely use our standard deviation formula. Okay, normality, again, we didn't hit the 40 number. We don't have the data to actually graph it, but we'll just for now say, oh, it should be good, right? Okay, and lastly, it just says a sample, so we'll just assume it was a simple random sample. All right, now get our z-score, and again, we have a one-sided alternative. Okay, so we want the probability that z is greater than. Sample was 58.75 minus the supposed parameter over the standard deviation. Okay, work that out and you'll have your z. We should get a z of 1.41. It does not exceed the z star. Okay, so that's why our p-value came up short. We did not reach a p-value small enough. Okay, again, we have evidence, it's close, but not quite there. So we conclude there's not enough evidence to say that the average paperback textbook is above 57.50. Okay, so we can't reject the null hypothesis. All right, let's do one more warm-up. Oops. Again, pause it, give it a try, see if you can get it right on your own. Okay, we have a claim that the average yearly sell, okay, so that's our null hypothesis. Okay, nothing here says one-sided, so our alternative is two-sided. Okay, we've got a mean of 2315. We've got a sigma of 75. Our sample size is 30. And then they want me to test the claim at two different alphas. Okay, so not a big deal. Just get your p-value and you can compare. All right, checks. There are at least 300 private high schools, so that's good. Okay, again, we don't have the data to check for normality. Our sample size is 30. We would prefer it to be larger, like 40 or bigger, but for now, we'll just say it should be. Okay, so the central limit theorem. Should provide approximate normality of the sampling distribution. Okay, and it just says again, a sample doesn't say what type of method was used, so we will assume it was a good SRS. All right, now let's get our z-score. And again, this is a two-tailed, so we're gonna double our probability, okay? So 2 times the probability that z is, now here's where I do look. My x bar was less, so I'm gonna go less than. Okay, and somebody say, well, how do you know less than? Well, if you do greater than and double it, you'll get a probability greater than 1, right? So if that ever happens, you gotta go, whoops, went the wrong way, right? It's pretty simple. C75 or square root of 30. All right, so there you go, there's our work. Figure out what z that is. Apparently it is negative 1.83, okay? And that's what's interesting here. If, right, if we're interested in a 10% alpha, well, we have enough evidence, right? If we're interested in a 5% alpha, we don't, right? Because our p-value is between 5 and 10%. So depending on your alpha depends whether or not you should be rejecting this null hypothesis, okay? So at a 10%, we get to reject the null. At a 5, we don't. And that's kind of the point why we did this as our last warm-up. That's the point of today's lesson, okay? How do I know, like, what's the magic, way of determining is this enough evidence or not, right? So we have to realize that if we just walk around saying, oh, we reject or we don't reject, that's not that telling, right? Giving a p-value is much more informative. It's much more telling than just saying reject, do not reject. Okay, so a more modern approach is to state your p-value. So on this last problem, 6% is your p-value, and say, oh, that's moderate evidence, right? I have evidence. Whether 6% is good enough, well, that's kind of up to you to decide, okay? So again, let me stress, don't say, oh, 5% is the be-all, end-all, because let's talk about that for a minute, okay? Let's say I have these p-values. Let's say I have a p of 0.050001, and I have a p-value of 0.004. 0.4999, and throw another 9 in there. Okay. Is there really any difference between these two p-values? Okay. No, these are basically the same, right? It's the same amount of evidence here. Yet if I just go, oh yeah, 5%, this one exceeds 5, this one's below 5, so we would get two different conclusions, even though it's really the same amount of evidence. Okay, and that's the point we're trying to make here. Don't just focus on 5% as a be-all, end-all. Report your p-value and say, we have roughly 5%, p-value. This is, moderate evidence to reject the null hypothesis. Okay, versus, okay, these two are the same. These two are different, right? Yet both of these would reject, and this one would fail to reject under a traditional 5%, when in reality, it's these two that are the same, not these two, right? This one down here is really strong evidence, okay? So that's the idea. In this lesson, 10.3, we're kind of going to take away the whole alpha of 5%, and we're just going to state our p-value and say, this is really strong evidence to reject, right? This is moderately strong evidence to reject, so we're not going to have like a line in the sand. And so that's the idea. We have a rejection region, and rather than saying, hey, we reject and leave it at that, we're going to kind of talk about where we land in the rejection region, or where we land as in respect to the cutoff. Okay? So, and the other thing to realize is there is no such thing as a statistics fairy that would fly down and tell you, hey, use alpha of 5% on this one, use alpha of 1% on this one, right? That doesn't really exist. So when you are the person out there doing the research, you have to kind of choose your own level of significance, right? What are you gonna say, hey, this is good enough evidence? Okay. So how do you do it? Well, you ask some questions. Your first question is, how plausible is the null hypothesis? Remember, you got to try to overturn that with evidence. So if it's very plausible, you're going to need more evidence to overturn it, right? And how do you determine plausibility? Well, have other people already researched this, right? Is there already kind of a mountain of evidence leading towards a certain direction? In which case, it's going to take a lot more to overturn that, versus no one's researched this before. You're the first one, okay? Next, what are the consequences, right? So one easy thing to think about would be in a medical setting, right? You're testing, say, a new vaccine, right? Well, what are the consequences of pushing out this vaccine when it's really not as effective as you expected or you hypothesized, right? Who knows? I mean, if it's life and death and it has a little less effectiveness than your null hypothesis thought, well, is that a big, negative consequence? Versus no vaccine at all, right? Or are we talking about possible side effects to a vaccine or a drug treatment? And one of those possible side effects is really nasty. Well, now all of a sudden, right, the consequences are different. So look at the consequences and use that to kind of guide you as far as how much evidence you need, right? If it's a life and death situation, then the level of evidence, depending on which direction you would lose life, changes greatly. Okay, now, this is very important. If I have a ginormous sample size, I can have just the slightest difference from the null hypothesis trigger significance. So let's just make up an example. Let's say I get an argument with one of my students. I say, hey, the mean GPA for my students is 4.0. Right? And somebody says, no way, your students have a mean GPA less than 4.0. And I say, okay, well, let's go figure this out. So we get a sample, and we get a sample mean of 3.99, and I say, oh, that's 4.0. I'm pretty much right. But let's pretend that the sample size was, I don't know, really large. Let's say 900,000. I know I don't have enough students for that to be the case, but we're just pretend. Okay. Now, when I get my, and I need a standard deviation. Let's say my standard deviation was 0.1. Okay, so now when I do the test, my z-score is going to be tiny, or not tiny. My z-score is going to be off the table. Okay. So what is that? 0.01 divided by 1 over. Okay. So my z-score is negative 94 something or other. Right? Doesn't really matter. Crazy small probability. Even though, I would argue 3.99 versus 4.0 is really kind of the same. Okay, so this is the idea. If you have a massively large sample size, any deviation from the null hypothesis will trigger a small p-value just because the sample size is so massive. So be careful if there's a huge sample size. Okay, this is a trick, by the way, that some companies use. Like, let's say I'm trying to come up with evidence that my weight loss treatment is effective. Well, what I can do is have a massively large sample size, and then if I get any weight loss at all on average, I can say, hey, look, I have evidence, I have a small p-value. I have evidence that my weight loss treatment is effective, even though the average person lost half a pound, right? Who wants to spend a ton of money for an average weight loss of half a pound, right? No one. But that's the kind of thing they put in the fine print, that the consumers won't see. And they'll just say, oh, yeah, there's evidence that this is effective weight loss, right? Doesn't say how much. So again, be careful of sample size. And that's what we're saying right here. We can have a difference, but it's a difference that's so small it's of no practical value, not important. So always actually compare things using a little common sense. Don't only plug things into your formula and get, whatever p-value. You're going to do that anyway, right? But also say, hey, yeah, I have a difference here, but it's of no practical value. Okay. Also, don't forget the things that we learned way back in the beginning of the class, right? When we have data, right, if it's not just the stats, if you have the data, please make a graph or two. Also, don't forget confidence intervals. So if we're talking about means, go ahead and give a confidence interval. Okay, now, of course, the other direction. What if I have a really small sample size, right? A really small sample size is hard to trigger your test, right? So be careful when I have a small sample size. I might have quite a large practical difference between the null hypothesis and my sample mean, but it doesn't trigger the test. When that happens, you need to notice, well, it could be the sample size here that's tripping us up, as opposed to the fact that, my null hypothesis is actually correct. Okay. So be careful that either way, sample size too large or sample size too small. And of course, if your sample size is too small, see about taking another sample and getting a larger set of data. Okay. Also, significance tests are great. They're wonderful. They're great tools, but they're not always valid, right? issues could be your sample size is too small, too large, etc. The data could be poorly collected, right? We could have bias in our data. It could be that we just happen to, by chance, get a massive outlier or more than one outlier in our data set, and because of that and the sample size, we're getting a result that shows significance when really it shouldn't show significance. It was just random chance. And this one's really important. Never test a hypothesis on data that suggested that hypothesis, right? So if I just have this data set and I go, wow, that's interesting. Why did my period 2 score so much better than my period 3 on this last test? Okay, and so then I go, I wonder if it's statistically significant. So I run the test. Well, I've cheated, right? I already saw that there was a large difference there, right? I need to run and set up my argument before I have my data, right? Using the data to set up my argument is backwards. If you go around looking for rare results, and then whenever you find a rare result, go, aha, there's a rare result, let's test on that, you're cheating the system, right? The system is based on random chance. So if you're cherry picking data sets, of course you're going to find significance, right? 1 in 100 data sets will, on average, have a p-value of 1% or less. Okay, so you can't do that. That's cheating the system. You need to have the null hypothesis and the alternative hypothesis set up first. Then you need to go out and collect good, unbiased data to test. Okay, not the other way around. Data does not come first. Data comes last. Okay, and this is kind of the same point I'm making. Okay, we need good, randomized, unbiased data to do inference. Okay, because this is probability based on random chance. We don't want to cheat that. All right, last thing. It is incorrect to run a whole barrage, a whole battery of tests all at once. If I run 100 tests at once, well, random chance says 1 in 100 should have a p-value, less than or equal to 1 on average, right? It's not a guarantee, on average. 5 out of those 100 should have p-values less than or equal to 5% on average, right? So we can't just run a whole ton of tests and then cherry pick, oh yeah, these couple showed significant results, and then say, therefore, they're significant. No. If you're going to run a whole battery of tests like that, you then need to do a follow-up, collect a whole new set of data, and test only on that one item that you think, okay, this could be, a significant item here. So again, this is something I like to ask about on our test, because it's a common thing that people will do. They'll just run a whole barrage of tests and cherry pick results. You can't cherry pick your data sets, and you can't run a whole bunch of tests and then pick out the ones that showed significance and say, aha, my treatment's effective against this. Could just be random chance, because you've cheated the whole idea of probability. If you do something enough times, eventually you'll get a rare result. All right, that's the end of the lesson.